the Department of Physics at IIT Roper, and today probably some of the parts which I will be discussing can go over your head. So bear with me, because if it's not going over your head, then I didn't work hard, because this is 10 years of my work. So you have to respect that thought, respect that thing that you cannot understand everything. But I will try to give you the glimpse how this computational materials physics works. Okay, and currently you see this picture. The computer is getting more powerful day by day, and even powerful than human brain. Maybe using the machine learning, artificial intelligence, and neural network. And before going to the details, let me talk about a bit information about the Department of Physics. So this is a very nice entrance of IIT Roper, which is situated close to the bank of Satluj River, and I would say it's quite natural place. No hustle like your college. You go outside and you do not have place to park the car. So we are lucky in that sense. And this is the big building recently came up. It's a giant structure of concrete. It contains 200 offices and so various research labs for 6 departments. So it's a very nice place for, you can say, collaborative research, where you can have the ideas from the physics, you can the biosciences, material engineering, mechanical engineering, and civil engineering, as well as mathematics. So and then we talk each other crossing by, and all of our offices are on the same floor. Then labs can be varying from in the different floors, ground floor, first floor, but the faculty offices are the same floor. And our department, the physics department, was it started in the same year when IIT Roper was incubated in 2009 with 2 faculties. But currently we are approximately 23. Soon we will be 25, I hope, hopefully. And currently in the Department of Physics we are running 4 different programs. One, of course, the BTech program for engineering physics, which is a combination of electrical engineering and physics. MSc, this is MSc Physics, standard MSc Physics program, and PhD, which is the integral part of any IIT system. Apart from that, we recently started this BSc B.Ed program, which is the, you can say, the guideline from the government of India to train the teachers for the schools and colleges. And if you have younger brother, younger sisters who are just in 12th grade, this is one of the nicest opportunity. If you are not going through JEE exam, there's a very simple exam called ITEP. You qualify that exam, you get opportunity to pursue Bachelor of Science along with the B.Ed degree. So it's a 4-year program where you have BSc plus B.Ed. And you can be specialized in physics or chemistry or mathematics. And you can say approximately 50% of our population in physics department comes from the PhD students. They are the backbone of whatever we are presenting today, all of us. They are the people who are working hard day and night for those things. And in the Department of Physics we have thrust areas. Currently all of us are coming from the condensed matter and material science. Then we have a very strong group in light matter interaction in quantum information, nuclear physics, and gravity and string. This is the thrust area currently we have in our department. And now about me and my group. My group works in the various areas. So we use computer as a tool. Like you go and perform experiments in your lab, we use computer as our lab. So we carry our lab with us everywhere. And then we, in our group, what we try to do, we try to develop new methods. How new methods can help you to understand the material science. We also work in rechargeable batteries, optoelectronics, high throughput calculation. High throughput calculation is the benchmark for the AI and machine learning. This is the foundation where you do a lot of calculations, collect the data, and then plug it into the artificial intelligence algorithm, and predict new things. Quantum transport, you must have studied if you are a MSc student. There are many kind of in semiconductor you have drift and diffusion, but you go to the nanoscale, then the transport there is no scattering. So it's called quantum ballistic transport. That is something we can calculate. And optoelectronics for the solar cells, and photo detectors, photovoltaic, and as well as the functional material. functional material can be used in many applications. Some of the applications my colleagues will be talking about probably after the lunch when they will have some energy. Okay. Okay. Nowadays computers are taking part everywhere. It's a part of our life. You can say that all of you are having mobile phone, and trust me, your mobile phones nowadays are powerful enough to run standard computational material science codes. You can install the code on your phone, and you can run and you can predict the material's property even in your phone. And this is a very peculiar field. Couple of days we were having PhD interview in our department. So most of the students coming from the university, what they want to do is a condensed matter experiment. Okay, so it's quite disheartening to us. But there are two main fields in research for centuries now. It's experiment, where you behave like addition. You mix and match things and predict new materials, predict new properties. You can define new properties. And then there is a theory. Theory can formalize things, which can tell you what exactly this experiment is talking about. But in recent surge of computer power gave rise to the new field called simulation, where you are in between the experiment and as well as theory. So you take the equations from theory, code it into computer, take information from the experiment, plug into those codes, and do miraculous things. Like graphene. Graphene was predicted much before than it was experimentally synthesized. There are many materials which have been predicted by computer, and after that experimentalists went to the lab, they got their hands dirty and then tried to synthesize those materials and predicted and then measured the property of those materials. And one of the pillars, because this is bedrock for the modern day material science, or another way I would say, this is the workhorse, density functional theory. In 2017, 2014, there was a paper published in Nature called Mountain of Paper. The paper mountain, and this paper collected the information from 1700 century until 2014. They went through all the publications and they looked what are those publications which are most celebrated. And out of top 100 papers, 12 were coming from DFT itself, from one field itself. 2 of the papers were in the top 10, and this number was in 2014. And after that, AI and machine learning took over really fast, and DFT is the foundation for those things. You need data, and data comes from DFT, either from experiment. How does it work? Now, these things are complicated, I understand, and these equations are also hard for me. I never want to have those equations, but this is my life. Okay? So, whenever you try to understand the material property, whenever you try to understand the electronic structure of material, there are electrons, there are nuclei, and then you think about constructing the Hamiltonian. If you are an MSc student, you know hydrogen model. What do? You try to understand the kinetic energy and potential energy. These are the two terms in Hamiltonian. So what we try to get is the kinetic energy of electrons, kinetic energy of nuclei, electron-electron interaction, electron-nuclei interaction, and nuclei-nuclei interaction. Last three terms are the potential energy, and the kinetic energy of nuclei, kinetic energy of electrons are the kinetic energy. You have the Hamiltonian. Now you can go to the very famous Schrödinger equation and try to solve that. And as an MSc student, you solve it for hydrogen molecule. But if you go think about having 200 electrons, now you will have 200 equations to solve all together, and this is one of the troublesome tasks. And these Hamiltonians cannot be solved even in the computer. It's very hard. So, as a mathematician or as a physicist, what we do is we take the complicated part of mathematics and try to do approximations. So, you try to reduce the complexity of the problem in such a way that your problem becomes simpler but doesn't lose the information. And that you can only do if you understand the physics very well. So, here you clearly see the nuclei are very heavy particles. Electrons are lighter. So you can say nuclei is moving slower than the electron. So if you are sitting on the electron, you see nuclei as a static particle. nuclei is not moving. If nuclei is not moving, we can ignore the kinetic energy term from the nuclei. So there is no need of that. And you can also exclude some of the nuclei-nuclei interaction, because we want to understand the electrons property, how the electrons are behaving in the system. So after some approximation, I will not go much of the details. Oppenheimer, he gave the Born-Oppenheimer approximation, and he constructed the Hamiltonian, which is very simpler considering these approximations. And he also said whatever property I want to calculate is for electrons. So he decoupled the electron wave function and nuclei wave function. So our problem became purely electronic. Nuclei is not there anymore. And then came Hartree. Hartree, what he did, you say you have 9, suppose in this room there are 9 students. One student is looking at the rest of the 8 students. At the same time, the second student is also looking at the 8 students. So if I solve something for the first student, the second student may get angry. Okay, why not me? So you have to solve the system in such a way everyone is satisfied at the same time. And this is the complexity of this particular thing. This is the complexity of the computational material science. So to solve that, what Hartree did, he said, okay, forget about individual interaction. Let's think about the electron is being in a medium of 9 other electrons. So that is called mean field theory, and Hartree solved this equation in numerical differential analyzer, which is a mechanical machine. He and his father were running with the hand, and then they were trying to solve this equation to get the energy of lithium, and they got it wrong. Why? Pauli's exclusion principle. Probably you must have heard of, very famous principle. No two electron can have the 4 quantum numbers same. And this is something he was missing. He was missing the exchange of electrons. Later on, Vladimir Fock was a mathematician from Russia. Along with that, they solved this problem. They added one extra term here, and they also tried to have the Slater determinant. If you remember the basic quantum mechanics, wave function can be symmetric and antisymmetric. They considered the symmetric and antisymmetric wave function, and then they constructed this Hamiltonian and they solved it. And this was the groundbreaking theory, which still is the heart of the computational chemistry, not the computational solid state physics, but the computational chemistry, because they were dealing with the wave function. And if you think about the density is just a square of the wave function. Physicists believe in density, chemists believes in wave function. Okay? Later on, the Kohn found density functional theory. Walter Kohn and his student, they developed this theory in 1964, and for this theory, Walter Kohn was a physicist. He got the Nobel Prize in chemistry just for this theory. And if you see these cartoons, he said, okay, now all these cartoons are looking at each other. Let's put the blindfold. And when you put the blindfold and don't give the exact number, the one cartoon will feel that I am in effective medium of many cartoons. So this cartoon doesn't know, he or she, whatever that guy is, doesn't know who is surrounding me. But what he knows, there is a medium. I am in a water or something like in a room where many people are sitting. And he constructed everything. Constructed everything means he constructed the kinetic energy, he constructed the potential energy, nuclear-nuclear interaction, electron-electron interaction, everything from the density itself. Means there are like suppose 200 students, this is the density, and from that density you are figuring out all the information. That was he published 2 seminal papers in 1964 and 1965. And that's how the density functional theory was born. How does it do? How does it work in the calculation? You take a system here. Suppose there are experimentalists. They come to me and they say that, hey Vivek, I grew a new material, and this is the XRD of the material. This is the crystal structure of the material. I take that information, plug into the code, and then code says how many atoms are there, which kind of atoms are there. If there is iron, there is 26 electrons. If there is silver, gold, probably 79 electrons. Carbon, 6 electrons. So code will ask me how many electrons are there, and the code will understand if I give the kind of atom is there, carbon, nitrogen, oxygen, and then it will construct the Hamilton potential energy, and now it knows the kinetic energy, and it solves the quantum mechanical equation in Lagrange-Euler method. Lagrange-Euler method comes from the classical mechanics, and it solves it and gives me the energy. And everything is energy. If I know the energy, I can do many things. Energy means if there is one orbital or one energy level, there are two electrons. One electron can go up spin, other electron can go down spin. So only two electrons can stay in one energy level. This is the basic quantum mechanics particle in a box. But suppose I am saying there is a 20 electrons. There are 20 electrons, then they have to be arranged into many states, and each state can contain only two electrons. So if I know the energy, I can construct those states. And if I construct those states, I can predict the band structure. And with the band structure, you can define the magnetism, you can define the optical properties, I can define the Boltzmann transport, like conductance, resistance, whatever property you ask me. Just this diagram can tell you everything with some applied quantum mechanics, advanced quantum mechanics. So this last picture tells you about the optical properties, how this system can absorb the light, whether this material can be good solar cell material or not, whether this material can be good battery material or not. That is, all those things can be defined by this. But there is one catch, is this. What Walter Kohn did, he said, okay, everyone is blindfolded. If everyone is blindfolded, does not mean that interaction is gone. Interaction was there. How to treat those interactions? How can I can say that you don't recognize your father and mother, but your father and mother are there, right? Those parameters has to be there somewhere. And what he did, he said, okay, let's take exchange correlation functional. Exchange means Pauli exchange. Correlation means how this electron is moving and pushing everyone. Like if I am an electron, I am just running through, and maybe I can hit people here and there. Okay? All those interactions, he said, these are quantum mechanical in nature. Let's put some approximation, and that approximation was exchange correlation functional. This is a very beautiful theory. It can be 100% true if you know this particular one thing in the red ring, exchange correlation functional. And the funny part, no one in the world knows how does it look like till now. This is one of the most interesting research areas in computational material science. And everyone has their own imagination. Like you go home and then you say that there was an earthquake, maybe this was that, building was rocking like this, because you were not there. So we all are not there. We just speculate. And if the speculation is right, properties will be right. I can predict more accurate properties. This is something my research area has been, predicting the new method, new exchange correlation functional. And when Walter Kohn developed this method, and they started with local density approximation. Everything is density. There is an electron. An electron sees I am inside the density, medium. So Walter Kohn, what he did, he said, okay, electron can feel the density where it is sitting and only where it is sitting. Okay, and that was the local density approximation, and that is the mother of all the functional. Later on, this was developed in 1964. But later on, people realized if electron is only thinking about itself, the Pauli exclusion principle will not be obeyed, because it cannot complain to the other electron because it doesn't know who is there. So electron has to know where it is sitting, and also it has to know the surrounding. Then only you can predict the properties of the system. And then the generalized gradient approximation was developed. That says electron is sitting here and the decaying, suppose the density here and the decaying density here. So the electron sitting maybe few femtometer away can feel the difference. Okay, if I go here, there will be huge repulsion. If I am here, less repulsion. That is something they added. And that is you can say that was the best thing happened in density functional theory, the functional called PPE, and that one paper has been cited by 200,000 times, 2 lakhs times. means 2 lakh people in the world consider that thing to be true. And there is another functional called belief. Belief, chemist like, I don't like, I am not a chemist, so I will not go there. Okay? belief works very well with the solids. It started predicting bulk modulus, Young's modulus, you can say the optical properties, lattice parameter, a lot of things it was predicting perfectly right. But quantum chemists were not happy, because whenever you develop a method, you think about the error bar. Error bar was high. Solid state physicists can work with that error bar, but molecular chemists cannot. They want the perfect system. So they complain. And in the beginning I said molecular chemists or quantum chemists, they believe in the wave function. Physicists, they believe in the density. We believe in the finite number. We don't want to go into complications. So physicists were very happy, but chemists were not. And then chemists came up with another idea. Let's take something from chemistry, something from the physics, and mix it effectively and create hybrid. And that is called hybrid functional, and this hybrid functional changed everything. It's very expensive. If I can calculate PB in my laptop, if I have to calculate the hybrid functional, I need 20 laptops. So see the expenses. The expenses are 20 times more, but results are more accurate. So you have to think as a physicist or as a scientist, if you are having less resources, you have to do something which is less accurate. And if you are very rich, a lot of facilities are there, you can go and do expensive things. Okay? So you can also drive a Mercedes as well as you can drive the Maruti Alto as well. Right? So it depends on your requirement, where you live, how much resources you have. But and the funny part, this picture, this is called Jacob's ladder. That phenomena comes from Bible. But in Bible they say there is a ladder to go to heaven. So if you climb that ladder, you can go to heaven alive. You don't have to die. Okay? So one of the physicists, he came with a nice plan. And he said that, okay, all these approximations are improving. So there is a mother of approximation, and then all these are improvements. So he planned it in a Jacob's ladder on the basis of accuracy, how accurately you can predict the property. And you see that the hybrid functional are on the top here. These are all the hybrid functions, and this is the local density approximation. But without having the first ladder, the last ladder is not possible. You cannot jump through. So this LDA is prime. It's called the prime number. It's a 0 point where you start to, and that is the reason we still celebrate local density approximation very well. But one thing is very important here to understand. We are not talking about van der Waals forces, and van der Waals forces are equally important. All these material property, adhesion, whatever you do, everywhere van der Waals force is there. It's a very weak force, but yet effective. For example, if you see in these three pictures, this was the first picture is from I would say a story. Maybe it's true or not true. I don't believe in it, but I believe in the storytelling. And this guy was Shivaji's Senapati, and he went to win the Bhangarh fort. And there is a saying that he was having a Damayanti as a monster lizard. He threw the lizard to the wall, and the lizard got stuck, and they climbed to the fort, and they won the fort. That is the story circulated everywhere. If this story is not true, but the second picture is true everywhere. This is a small lizard at your home. It's hanging upside down in the roof. How? Because for a long time, although the theory has been discarded, but for a long time, they said there has been a small races. It's like hair. These hairs can create enough force through van der Waals interaction and can sustain the lizard on the roof. So individually these forces are small, but collectively it's strong enough to contain anything. Okay? The DNA, if you have seen the DNA structure, the DNA is called different component of DNA. They stack on the top of each other. And according to Hindu mythology and also from scientific community, our DNA can store the information since the beginning of the world, okay? Beginning of this universe. the first cell was born, the liquid crystal. Then on the top of that there was another liquid crystal, there is another liquid crystal, and all these crystals came together, gave the birth of the life, and after that we evolved from fish to monkey to human right now. But according to science, according to our mythology, our DNA can contains all the information. So if you can have Kundalini and whatever you say, you can gather all the information back. But my perception is not that. My perception is all these interactions are van der Waal interactions. So DNA is storing the information in terms of van der Waal. It's not a very, it's a magical thing. Very weak force, but having the information intact in your body, in your hair even. The last one, probably this guy is born with all the information. That is, he's very angry at the moment. But if you want to know about these things, you can watch this movie called Julie. Julie, it's a Hollywood movie, and the concept of that movie is the same. This girl has the information in her brain since the inception of the world, inception of the universe. Overall, this can be very important. This course is very important for chemists, biological physicists, synthetic biology, pi-pi interaction, and it also guides the self-assembly. Okay? It can guide the thin film. Why do we care? As a computational physicist, why should I care about this? I care about this because this is, for me, it's a bread and butter. You see, if I talk about the battery, everyone is having battery in their pocket, and your battery has one electrode called graphite. Graphite is the van der Waal layer, and then lithium goes into graphite and comes back. When it goes in, you charge the battery. When it comes out, you discharge the battery. So currently, all of your batteries are getting discharged because lithium is going out of this gas. It's a very particular gas. Okay, and this property is governed by the van der Waal forces. If you don't have the van der Waal in your calculation, you cannot predict this thing right. For a long time, physicists were predicting bad things only because of absence of the van der Waal force in the calculation. Van der Waal heterostructures, probably some of them will talk about, is any device. You talk about field effect transistor, if you talk about any other spintronics, MTJ, everywhere you are stacking the layers. And if you are stacking the layers, there is no chemical bond, there is a van der Waal bond. Okay? If it is the 2D material. If it is a 3D material, it is a different picture. The last one, the DNA sequences, I just keep it to remind myself I did something in PhD. So this is the picture from my PhD thesis, where DNA is going through the pore, and then you can connect it with the battery, and then there are two electrodes. You can do DNA sequencing. You must have heard about it. And this particular device works on the basis of the van der Waal force, because the DNA is not touching the electrode. It is going through the pore. Only the van der Waal force is playing a role to predict this current. If you don't have the van der Waal, you predict the bad current, and you will not be able to detect them. So the question is, should we really stop developing DFT without any van der Waal forces? Answer is, of course, no. We have to do it. And in DFT, the van der Waal forces are done in added in various ways. Simply, this van der Waal force is in between the two fluctuating dipoles, and the standard formula is C6 by R6. So R is to the power 6 says it's a very weak force. When you go far, it goes smaller and smaller and smaller. So effectively, if you see from this equation is very weak, but in couple of slides, previous slides, I mentioned it's very strong if it's accumulating. Okay. So in DFT, what we do, there is one way you calculate the energy of the system from all the equations and all, and add this term as extra term. It's called dispersion term. You see all the molecules and calculate the energy and add it up there. This is called parameterization. But no one likes it. Parameterization is not a good thing, because you can control the parameters. So how will you control the parameters? If you are not smart enough, you don't know what to do. And then maybe instead of adding 2, you added 20. And then your calculations will go back. There is another way to do that. I will come into the next slide. It's called VDWDF approach. Means everything is approximated inside is exchange correlation function. Okay. How does it look like? You have exchange, then you have correlation. We know these things approximated long back, and then you add one extra term, non-local correlation, but again you have to calculate it from the density itself. If you are not able to calculate it from the density, then it will be parameterized. So it should be from the ground state density, and for that these are the two fluctuating dipoles, and when they fluctuate you can solve this double integral in computer and you can calculate this term and add it there. And our jack of ladder van der Waals community, our method is on third. The top two are on the DFT, they are tight binding, so we don't bother about them. We bother about the third step. Okay? We are staying there, and we are better than the parameterized and non-parameterized solutions also. Then comes the, I told you about many things. One is the GGA functional, one is the hybrid functional, and then we also talked about van der Waals functional. But at the same time, chemists again are not very happy with us because our van der Waals functional is not having any chemistry approach. So maybe we can design something which has hybrid approach and then van der Waals. So that is something I did in a few years back and called van der Waals density functional hybrids. Hybrids, Pauli exclusion principle. What we do, we say that okay, there is exchange. This exchange is not very good. So we try to take the exchange parameter from chemistry and say that okay, we separate the region. Up to this region, chemistry will work. After this region, physics will work. And then we do very carefully in mathematics and then code it into the computer. Once you code it, then we got this, it's called van der Waals DF hybrid. There are two types of hybrids. Not go into the detail. It's called range separation and the global hybrid. But the moral of the story is there is a hybrid functional which can calculate the van der Waals forces in inside-out approach. That's the takeaway message from this slide until now. And then comes the chemistry and physics part. The more probably you can understand, relate to this. Whenever you develop a method, whenever you say that I found new thing, you cannot, the world will not trust you. No one trusts you. They can only trust if you prove that this thing works. And that is something we did. We did it for 2 years continuously, making a benchmark set. We took a lot of calculations and we started calculating those systems and compared with the experiment a very high level of theory so that we can prove whatever we develop is right. And it was a very challenging task because we were running 2,500 calculations 50 times. So think about the computer which is running all these calculations and about me also who is just asking computer to do the calculation. Okay? So there are many sets. Yeah, you can the very small reaction barrier, small molecular interaction, long molecule interactions, surfaces. It's all this benchmark is made of all those things. Okay? But the question again came. DFT has advantages as well as the limitations because how you implement it. Again, physics and chemistry come on front of each other. Chemist thinks into wave function approach. We think in the density approach. In density approach, your solid state physics comes into picture. Block function, block wave, quantum mechanics, Crony-Penny model. So what we do, we calculate the system in a periodic manner. They calculate system in the open boundary condition. They don't need periodic system. So when you calculate the system in open boundary condition, things are very easy, but computationally expensive. But when you calculate the system in periodic boundary condition, things are very complicated but cheap. Okay? So the question we ask ourselves, can we run all these calculations in our physicist way? The answer was not. We cannot. We can only run GMTKN 53. Two of the sets impossible for us to run because our physics approach doesn't allow that. But chemists did that. This is a very famous benchmark from one of the group in chemistry. And the question was, why we cannot calculate it? And very simple is OH molecule. You know OH molecule, right? If you take H from H2O, then you are remained with OH and with extra negative charge. OH minus. So oxygen has 6 electron or 8 electron, whatever you say. Hydrogen has 1 electron, but now there is additional electron. And our calculation doesn't know what to do with this extra electron, where to put it. This electron, whenever you try to calculate, we try to push the electron in the system, it bounces back. He says, no, I don't like the system, I will go away, fly away. It hits the vacuum floor. Probably, no, it's not here. It hits the vacuum floor again and again. Okay? And when it hits the vacuum floor, your computer cannot convert the calculation. It will not give you the right result. So we decided to stick with the 53 benchmark set, because 2 of the benchmark sets, there were like 30 calculations like this: S minus, OH minus, HS minus, all these small molecules with extra charge, and none of them we could calculate. Here you see, this is again you can say numerical method where you calculate some errors, percentage errors, weighted errors, and all those things in your MSc. So we did some tricks to calculate the effectivity of the functional. And if you see, my functional is AHCF and CH0P, and these colors are performing consistently good. Apart from this, probably I am a bit color blind, so for me it's hard to find the colors. Okay, I have to put a lot of attention on that. So probably okay here. Probably here we are not very good, and in one more case, in the last one. The idea is, whenever there is a reaction barrier, whenever the electron is coming or there is a transition from one molecule to other molecule, we are not very good. And there is a reason behind it. There is a reason called density driven error. And whenever you talk about density, you talk about physicists. Density driven error is our problem. We cannot solve it. This is probably more relevant to you. These are the 2 small molecules on the top of each other. There is no chemical bond. There is a strong large gap in between these 2. They cannot make any bond. There is no ionic bond, no covalent bond, nothing. But there is one van der Waals force pushing them close to each other. They cannot come closer than that. When they will come closer than that, then there will be some kind of repulsion, where the Pauli's exclusion principle will also play a role along with chemical bonding. Okay? And this is one molecule, and then we took it and then bend it. When you bend it, again you have van der Waals force, okay, in the bending area. Okay? Our bended area is from here to here. And then we try to calculate, this is an example, we calculated maybe 1,000 molecules like this, and try to understand whether we are calculating it right or wrong. So see, this is the intermolecular P, is called MAD. It's a error percentage are quantified into kilocalorie per mole, because chemists like it. Okay. So here you see our error bar is very low. We are calculating error around 0.45 for AX, CX and CH0P. On the other hand, most of the functional, most of their approximation, they are not doing good. They are far apart. They have error around 0.7 and 0.8. This shows that we, as a physicist, are better than most of the exchange correlation functions. Now the bulk property. Bulk property is like iron, cobalt, nickel, silver, copper, all these materials. We can calculate the lattice parameter A or B or C, and we can calculate the cohesive energy, whether they will cohere. There will be cohesive energy supporting the crystal structure formation, and we can also calculate the bulk modulus. And this is the Wheeling plot. Wheeling plot says if your Wheeling is fat and dwarf, it's not good in the real world, but in our calculation is always good, having very small and fat structure close to this line. If you are close to this line, then you are good. If you are going beyond this line, then you are bad. And these 2, the last 2 are my functionals, and if you see, we are very close to the line, and the last one is even fattier close to the line. This means, this shows that our functional can calculate the lattice parameter very well, bulk modulus very well, as well as cohesive energy. If these 3 properties can be calculated well, the electronic structure, density of state, which you have studied in your MSc course, and band structure, they can also be calculated very well. This is another one. These are the 2 extra functionals. and they are even better than our previous functionals. So you see, although they are not on the line, but their spread is very good. Their spread across a lot, you can say that they are still away from the line, but overall spread is good. And overall spread is good, and this, you can say the dot, this dot, white dots, this is a mean value. So mean value is not bad. Mean value is quite good for us in comparison to the PPE functional, which is cited by 200,000 people in the world in last 10 years. So this was the message to the world that whatever we are developing is better than whatever you are using beforehand, but comes with the price. It's expensive. It's expensive to calculate. Now we did some. How much time I have? 10 minutes. Okay, good. So I was doing this 53 benchmark sets, but the 2 benchmark sets were haunting me. I am a physicist. Why I cannot do this calculation? Chemist can do this. So we found another approach, and this is a very fancy thing. What you do, you have a molecule. There is an electron coming to the molecule, but molecule is not able to take the electron. We are trying to force it. It is bouncing back. So what we did in calculation, we put it into the water. Molecule is in the water, and electron is coming close to the molecule in the water, and water is putting some force. It's not allowing molecule to fly away, and water has certain dielectric constant. Well, how do we do it theory? How do we do it computation? We try to reduce the dielectric constant of the surrounding slowly, and we can go up to the very low level, and then we do this fitting. So we are starting from here, and then the 1 is the vacuum. 1 is the thing which we want. So we can calculate up to 2. 1 is hard to calculate. Then we polynomial fit, and we fit the value, and we can get that number. So now to get one number, we have to do 20 calculations. And now think about 1000 calculations. We have to do multiplied by 20 calculations just to get this one number. And everything we can do in automated way. We just submit the calculation, we go on the vacation in Greece and come back, our calculations are done. Then we can run another code which is written by us, which will take out all the information, give us maybe 30,000 of these kind of plots and the numbers, a table. And then we can take that table, plug it to our calculation done before, and then we can plot this. And with the 55 benchmark sets, we were very, very good. Our performance was much, much better than any other functional. Sorry. And this is before that method we applied. So this is 53 benchmark set, and this is with 55 benchmark set. These are all the functional, these are all the methods. So see, when we were not having this molecule in our calculation, these kind of molecule in our calculation, everyone is saying doing relatively better, but we were the best. But when we added the challenging molecule in our calculation, then everyone fall off the cliff. This is the highest value. Everyone fall off the cliff. Only few of us. This is 4-5 methods developed by our group. They are staying in the business, and rest of them are falling apart. Okay, and this is how you claim to the world that okay, use our method. Otherwise, no one is going to trust you. And you have to check your calculation maybe 30 times. Maybe you are claiming something which is not right. So all those guys will come back and bite you. Okay, you claimed it, and you claimed the wrong thing. Now, the last few minutes, probably I will give you the more relevant thing. It's called CO adsorption puzzle. CO is a molecule, carbon monoxide molecule. It's a very simple molecule. This is very important for the catalysis business. So whenever you do catalysis, you want to convert CO is very dangerous. You want to convert CO to COOH, which is not harmful, or CO2, which is less harmful. This is the catalysis. Nowadays, catalysis is in the car exhaust, where the gas is coming out, and then this catalysis converts all those gases into less harmful gases to reduce the global warming. Okay, for that, platinum is used. Platinum is very expensive. Even I cannot buy jewelry of platinum. It's that expensive. Okay, it's expensive than gold, but platinum is it's a miraculous material for catalysis. But which is just to tell you the challenge. what happens when CO molecule goes to the surface? There are, platinum is a CC lattice. So if you construct a surface in 111 direction, if you know how to cut the plane in the 111 direction, there are three spots. One top side, one hollow side, and one FCC hollow side. So whenever you calculate, doesn't matter what method you use, doesn't matter what code you use, this molecule always goes to the hollow side. But experiment unanimously suggests this has to go to the top side. Now think, if you are not able to calculate the adsorption, how can you calculate the whole equation? How can you calculate the catalytic property? It's not possible. And that was a challenge given by Feibelman in 2001. It's called COPT puzzle, and also Achilles heel for the DFT. Achilles was a warrior in Greece. So his bone here was cut down and he could not walk. This is called Achilles heel. Okay? So this is for DFT, this has been Achilles heel. To understand that, first we need to understand the adsorption of CO molecule on the surface. How does it happen? And that model was given by Byholder in 1964. It's such an old paper. Still today people cite that paper because that was a groundbreaking explanation of adsorption. CO molecule has 2 sigma orbitals and 2 pi orbitals and 5 sigma orbitals. Pi orbitals are like this, splitting the wing. Okay? And sigma orbitals are vertical. So when this molecule goes to the surface, then there are two kind of things happen. First, sigma orbital donates electron to the surface atom. Okay? At the same time, these pi orbitals, they are ready to take electron. This is a competition between these two. Sigma orbital is giving the electron, pi orbitals are taking the electron. If pi orbital will take more electron, adsorption will be stronger. If sigma is very hard to, sigma doesn't want to give electron, sigma wants a harder. It doesn't want to give the electron. So if sigma is strong, the adsorption is weak. Now the problem happens when you go to the top side. You are in direct contact with the sigma bond. Okay? But you go to the hollow side, your pi orbitals are going close to the surface. Then suddenly the CO molecule is taking more electrons. And that is the reason DFT predicts always CO will go to the hollow side, not to the top side. And with that, you cannot predict any property. You cannot do the catalytic calculation. And the reason behind that is density driven error. You cannot predict the right density. And whenever the density comes into the picture, physicist comes to the picture. Okay? We try to use our functional. Our functional has an approach of chemistry, approach of physics, and van der Waals. All of them are there at the same time. So we thought, okay, let's test this puzzle and see what we get out of it. And question is, did we solve the puzzle? This puzzle has also a part called surface energy. You have to calculate the right surface energy. Okay? Because the answer is here. Most of the functions, anything above that line is bad. Anything below that line is good. These are our functionals. These are our old functionals. They are not performing well. These are our new functionals. They are doing better job. So we can calculate the better adsorption. And if you can calculate the better absorption, probably I can do some calculation for this guy here who does catalysis in experiment. Otherwise, he will not trust me with my calculations and he will not ask me anything. Okay? So, for the conclusion, in DFT, in the computational physics is still finding an exact exchange correlation functional is a challenge. It's very hard, and research, a lot of people in the world currently must be doing some research on it. So our job as a student, as a physicist, as a researcher is to find a good exchange correlation functional. Develop a good exchange correlation functional. And to develop some exchange correlation functional, find a real challenging problem to solve, like COPT puzzle, adsorption of CO molecule on the surface. And overall this conclusion, I am again not going to boast about me, but this is the thing we did better than many people in the world. And with this is my conclusion. Just to announce something, recently we got some big grant where your Central University Dharamsala is also part of it, called DREAM. It's a 100 crore grant where Central University Himachal SPU is the part. And in this we are going to announce few positions, and this everything is imbibed into, you can say, advanced materials where physics, chemistry, material science, mechanical engineering, electrical engineering coming together and to perform some experiments. For that we will have few PhD positions, few JRF positions in future, and this our consortium is mostly located in northern part of India. So you can approach any of these universities, Bareilly, Punjab University, Central University, Rajasthan, Kurukshetra, and Katra, Mata Vaishno Devi University, Katra. And currently this is my group at IIT Ropar who are doing all those calculations when I am here, probably, if they are motivated enough. Otherwise, I don't know what they are doing at the moment. With this, I would like to thank you, and I will be happy to answer any questions you have.
Thank you, Dr. Vivek. Any question from the audience?
So you can ask anything, not from this research, because that is something I don't understand either.
Yeah, something about PhD.
Yeah, I will be happy.
Or higher studies at IIT Ropar.